So, good morning. I won't even sit down because, there are various introductions and I don't want to add one more. So, as you probably know, Jocelyn Burnell was awarded the Matteucci Medal, which is probably the most important prize given out by the Academy. It goes back to, I think, 1850, more or less. And it has been awarded to to many of the important physicists in the last 2 centuries. So when I knew Jocelyn for other reasons, and when I read that the committee that was made up by Paolo, Giorgio Parisi, and Maiani awarded it, I was extremely happy because for personal reasons. And and then I looked around and I discovered, in fact, she was the first woman to be awarded this prize after 1907. And in 1907, Marie Curie got the prize. So this is another instance of the importance of Jocelyn work and also of the very bad attitude of physicists towards women. Okay, and so I think that I won't say anything anymore because there are two introductions. One by Marco Tavani, which will be more technical, and the other one by Elisabetta Sier will be more, biographical and colorful. And then maybe Paolo will be the chairman of the rest. Okay. So I wish you a pleasant morning. It's going to be a short and I'm very happy to be part of the event. So I give my mic to Marco. Okay.
Yes, just a few words of introduction. It's a pleasure, of course, for me to be here. And also on behalf of the National Institute for Astrophysics. And I'm happy to say in some way that Italy really loves pulsars and neutron stars. Okay, so there's been a long tradition over the decades of a lot of scientific interest. Franco Pescini, Niki D'Amico, Nanni Bignami, just to mention a few of the people who are not with us anymore, but in this room there are lots of their pupils and followers of this religion, this pulsar religion. So to our fellow mathematicians, I can say that a neutron star is like the city of Rome. There is this annular highway that we call Grande Raccordo Anulare, which is more or less circular. So the mass of the sun concentrated in a sphere with a diameter of about 20, 30 kilometers. The sphere rotates, is magnetized, rotates sometimes very fast. For example, the pulsar in the center of the Crab Nebula rotates 30 times a second. So imagine Rome, which rotates 30 times a second. So it's an incredible amount of power, and indeed from the variation of the period, so the P dot, the variation of the period, we calculate the energy, the rotational energy that the ball loses every second, which is about 100,000 times larger than the luminosity of the sun. So we are talking about huge energies, peculiar objects, which are at the end of the evolution of stars. And they are detected in radio pulsars at the beginning. And we are indeed honoring today the discovery in some way and the accomplishment of Jocelyn Burnell. But also they emit, just because of their complicated pattern of currents and the phenomena in this sphere which rotates, accelerates particles. Therefore, it's a wonderful accelerator of particles and produces, by the way, the theory predicts, and the observations also confirm that, a wind of electrons and positrons. So it's a machine, it's an incredible machine, which can be studied both from the point of view of nuclear theory, because it has the density of the nucleus, or even higher than the nucleus. So it's the last barrier, frontier in some way, before the gravitational collapse. So matter can resist up to a point, and then there is a black hole. So neutron stars are the stage before the black hole. And but then they accelerate particles, and it depends on their environment. So sometimes they are isolated, sometimes they are with companion stars, so that in binary systems. And when they are in binaries, there is a lot of firework, because then the companion star provides a sort of target for this wind, which emanates from the pulsar. So you have an interaction of the pulsar wind with the companion star. So there are lots of a large variety of phenomena you can imagine, the kind of fireworks that you can do. So it goes from radio astronomy, very precise timing. You will hear today the applications of the wonderful monitoring of pulsars that can provide a lot of information, also at the cosmological level in some way. So it's a really wonderful tool, but also high energy astrophysics. So because they accelerate particles, particles radiate, produce X-rays, gamma rays, up to TeV gamma rays, which are really the maximum energies that are detected today. And then when they interact with the environment, either a companion star or the interstellar medium, or the medium around them, they indeed shock the medium in some way, so the pulsar wind is stopped and produces acceleration at the site where it interacts with the environment. And so they are today very energetic sources in our galaxy, which have been detected very recently. And they actually are producing gamma rays up to almost 10 to the 14, 10 to the 15 electron volts, so really the largest energies ever detected. And they are believed to be produced by the so-called pulsar wind nebulae, which are these kind of strange situations where you have the pulsar which is inflating the surroundings, and then it stops somewhere. And then being stopped produces a lot of gamma rays. So it's really a wonderful set of situations. And last but not least are the connection with black holes. So pulsar aficionados have been searching for a combination of a radio pulsar and a black hole in a binary for many, many years. Okay. So far, they have not been successful, but I hope that at some point they will detect a black hole with a radio pulsar. If you could detect that, you can imagine that the pulsar rotates. The black hole, of course, will give a lot of effects on the orbit based on general relativity, and therefore you can study general relativity with exquisite details using the pulsar as a probe. But now we have gravitational waves. And so our cellular phones these days are bombarded with messages from LIGO. Virgo, there was one just a few days ago of an event detected in gravitational waves, which is attributed to a black hole and a neutron star. So when these things happen, everybody looks for possible radiation from the coalescence of a black hole and the neutron star. So far we have not detected yet, but that would be a fantastic development of the next months or days or years. So it's really a wonderful occasion today to celebrate, of course, Jocelyn, and to have wonderful colleagues today which can tell us about these incredible machines. Thank you.
So I prepared a PowerPoint with the main facts about Jocelyn because I've been knowing her for 18 years. And the first time I met her, she was not as famous as she is now because she won the Breakthrough Prize. Jocelyn is known also for being one of the scientists who almost won the Nobel Prize. what happened is very interesting, actually, from the human point of view. She was born in North Ireland, and then she studied at the University of Glasgow, where she got her bachelor degree. And after that, she was enrolled in Cambridge University, where she met a very smart advisor, Tony Hewish, who was at that time studying with a special machine she helped in building a scintillation array. And they were actually studying the quasars, which were not the pulsars. So she had the duty of checking 29 meters of paper each day to find out if there was something strange in the data that they had collected. And she noticed, not on English, that there was what was called by the press a bit of scruff, means something strange. At the beginning, they thought it was some extraterrestrial signal, some person on some mysterious galaxy who was trying to connect with us. But she soon detected the fact that it couldn't be that. It was very regular, like the lighthouses of the universe. It's like a lighthouse. A lighthouse gives this beam regular every certain number of seconds, and she noticed that this was going on. Then at that point, she and Hewish published a paper on Nature describing their findings. But Hewish was not convinced about this, and so when later on, quite later on, 1974, he was awarded a Nobel Prize with Martin Ryle, who was an astronomer of Cambridge. Her work was not recognized. I think this is really not the only case in the history of women in science. We have other cases, I won't mention them, but it's a sign of what usually women have to go through in order to be recognized with their research. So, Claudia's gone. Next one, thank you. So Marco luckily said something about pulsars. Of course, I am a mathematician, I am not an astronomer, and I learned what pulsars are just studying the story of Jocelyn Bell Burnell. They are really a fascinating celestial body. This fact that they emit these beams makes them really beautiful from the point. There is this picture here which gives an idea of how fascinating they are. And what happens is that they are born when a star explodes. All this energy, this incredible energy. And this for us mathematicians is something out of our range of thinking. We don't deal with energy. Especially me, I am an algebraist, so I deal with abstract objects. So finding something of this kind is really something new. So next, thank you. I skipped just the main facts. She has a CD which is about 10 pages, so it's useless to me. But something has to be said. She had many. She married at a certain point, and in order to follow her husband, she moved from one place to the other. As she is extremely smart as a scientist, she could find proper position. So as you see here, she was at the University of Southampton for a certain number of years. University College in London, and she was also in charge of the Royal Observatory in Edinburgh for a while. There is a portrait of you in that place, right? I saw the picture of the portrait. So now she is the Chancellor of the University of Dundee, and she's a visiting professor of astrophysics at the University of Oxford. So she had and many other positions. So we won't get into detail. She was moving around. And each time she started something new, because, for instance, when she was in London, she was going to a place which was out of London, if I remember well, and they were working all the week. She had to take care of something that compelled her to stay there. Also on weekends, she was working all the time, but she liked it so much that she did it. Next, thank you. So now, the controversy of Nobel Prize, just a few words, because it's something that really is extremely bad in the history of science. the fact that they didn't recognize their work means that, okay, at that time, they made also jokes about this. She was saying to these people with whom she was working, look, I have these findings here. And they were saying, it's not like that, it's different. It couldn't be that you found actually new stars. But she did. And that was only the first time she found one after she found other pulsars. So next, after 44 years, she won the Breakthrough Prize. The Breakthrough Prize is a beautiful idea, which is due to Mark Zuckerberg of Facebook and the inventor of Google. So you know that they have plenty of money, and they organize this prize, which is given not only for a breakthrough discovery, but also for things that have been discovered some time ago, but which are extremely important. And everyone at that point knew that she found something extremely important, because these celestial bodies are studied even now, and so it's full of, there is a lot of research about them. So she was, and the prize has another interesting feature. It's a $3 million prize. So this means that she could, what she did with it, she simply gave it to young researchers in order to face, especially women, in order to face a new career in astrophysics. I think this is a wonderful thing that she did, really important. Next, this is nice, because Jocelyn at a certain point was made Dame. As a matter of fact, I put the title Dame Jocelyn by the Queen Elizabeth. We all know, I guess, even if you are not British, that in Great Britain, this is a real honor. I mean, we don't have the same thing in Italy, unluckily, but well, we have something similar. But it's not like this one, because when you call someone a lady dame or a man sir, it means that he actually did something extraordinary for the country. And she did, as we know. So she had this honor, and many other honors. Also, the list of honors is very long. So I just mentioned 2 or 3 things: the gold medal of the Royal Society and the Copley Medal. This struck me really very much, because the only other woman who won this Copley Medal was Dorothy Crawford Hodgkin. She was the wife of the famous Hodgkin of the terrible disease, and herself, she was a Nobel Prize. So, I mean, she's in very good company about the Copley Medal. Next. Now, last but not least, the Matteucci Medal. So, Matteucci, when he died, left amount of money, which by using a decree of the name of the number of decrees should be up there. I think if I did, yes, decree of 10th July 187. Now, why this is so important? It's important, at least my point of view. I deal with gender problems in science. She was the second who, as the president said, after Marie Curie. I mean, after Marie Curie, no woman won this medal. 70 medals, 70. And she's in very good company. As you see the names there: Antonio Pacinotti, Thomas Edison, Guglielmo Marconi, Marie Curie, and on and on. Many Italians, luckily. So, and I think this is a big honor for her. She deserves it. And she can put this in the list of the many medals and honors that she received. Last but not the least, the last one, there is this lovely picture I found on the web. It was a commemoration of the University of Rutgers in the United States. And she was there, and they are, she has this honor. And you see Barack Obama, the side of the country, with this lovely expression, thinking that his country is very important for science, and this is absolutely true. So this is just to say thank you, Jocelyn, really, because I am a big admirer of her. I think she did a very good job in science, but besides that, she's a very nice woman, generous, And you know that she was a teacher at the Open University. I don't know, I think you know what the Open University, they do it online. And she was taking care of an incredible amount of students. She has she's a wonderful teacher, by the way. Check, you'll find out this after. So thank you very much, and thank you, Jocelyn. Okay.
Okay, so we can start with a presentation from Andrea Bussenti now, and he will tell us about the news and the interest of these pulsars. So, will be very interesting.
First of all, thank you all for having invited me to remind something of the consequences of the wonderful discovery done by Jocelyn, to whom we really have all of us have a huge debt of gratitude, because this discovery allowed all of us to perform a science investigation which we loved since the beginning, still loving, since it has a lot of phases. And I'll try just to capture a couple of them today after a brief introduction in which I'll try to give you the picture of the many things that in a 3 hours long meeting I could have described, plus those which will be described by my colleague afterward. So the two previous contributions already remembered how Jocelyn has been the absolute beginner of this branch of science, with the small scruff mentioned before, which is there depicted, observed in the August of 1967. And it has been already mentioned what a pulsar indeed is, but let me show also a pictorial cartoon representing what's that. The word lighthouse just comes from the similarity among this kind of source of radio waves with the lighthouse we see in our port. The light is always on, but we see that once upon a while at every rotation, simply because the light points in different direction while the lighthouse rotates. So this is the basic idea, and to be a bit more precise, has been already mentioned by Marco. Basically, this is the underlying object is a neutron star, this incredible object, which also Nicola Bucciantini later will better describe, rapidly rotating and emitting these anisotropic beams of radiation. And Jocelyn discovered the first and another couple of them at the beginning. Now we went beyond 3,000 of this object. I just checked this morning the catalog, and the total number now is 3,268 of this object, known and counting, of course. There is a peculiar subgroup of them which is particularly interesting for doing science. They are called millisecond pulsars. The reason is that they rotate very fast, with even period slightly above one single millisecond, and they are created in this way after the initial explosion, which produced the neutron star, if the neutron star is in orbit with another star, under suitable condition, the companion star can pour mass towards the neutron star, spin up the neutron star, and produce a much more rapidly rotating neutron star than the rotation rate the neutron star achieved before. And these millisecond pulsars are less abundant than the global population, as you can see in this plot. About 1/10 of all the known pulsars are millisecond pulsar, but they are really very, very useful for a large variety of science activities. So, quickly reviewing some of them, the possibility of studying nuclear physics, basically the interior of the neutron star itself. This will be later discussed by Nicolò, and he will also discuss the possibility of using them, as anticipated as well by Marco, the possibility of using them as a laboratory of plasma physics, since they emit these accelerated particles plus powerful radio waves, which interacts with the surrounding material. But we can use them also, for example, for finding planets. The first 3 planet-sized objects ever discovered outside our solar system were discovered thanks to a millisecond pulsar observation done by Andrew Volshan in early 90s. And another interesting thing is that, have you seen this recycling, so-called recycling process, in which the companion star transfer mass towards the neutron star? This is a very peculiar stage of stellar evolution, which can really be carefully observed and studied thanks to the capabilities of detecting radio pulses from a pulsar. And another interesting point is the possibility of finding many of them inside the oldest stellar systems composing our galaxy and all the galaxy, namely the so-called globular clusters. They are ensemble of 1 million to few million stars, very compact. The distance among one star and the other is much, much smaller than the distance among our sun and the closest sun and the closest other stars. And so also the gravitational field there is very interesting to be studied. And with the pulsars, if you find many of them, I have a couple of examples here of 2 globular clusters in which almost 50 pulsars have been discovered, and another one which we are just studying this way. That's why I reported that, in which in the last couple of months we discovered 13 of them, and before there was none known. So when you discover so many pulsars so close to each other in a so compact stellar system, you can really learn a lot about the way that dynamics and even the classical physics works in this system. And going on, you can use pulsars for studying the interstellar medium. The space out there among one star and the other is not empty at all. There is a tenuous gas. Part of them is ionized, and thanks to the study of the radio pulsar, you can detect how much ionized gas you have along your line of sight. And when you have 3,000 of these objects, you can really reconstruct a map like that of the ionized gas in our galaxy. That is a cartoon picturing our galaxy from above, and the color corresponds to different amount of local ionized gas. The same way you can study the magnetic field in the galaxy, since the radio pulses are subject to various physical effects. One of them is the so-called Faraday effects. I don't want to enter in details, but is a rotation of the polarization plane of the radio waves while they traveling across an ionized medium. And so, detecting this rotation, you can infer the magnetic field along the line of sight and reconstruct the magnetic field in our galaxies, which is really very difficult in other way to be done. And finally, what I'll focus in the remaining 10 minutes are these two wonderful fields of research. First, study of gravity theories, and in particular, the most relevant, probably the most, the breakthrough across all the breakthroughs of past centuries, the general relativity theory by Albert Einstein. And on a second side, I'll briefly mention also the possibility of using pulsars, not for studying them, but using them as probes for detecting gravitational waves. So, why we can do all these wonderful things? Because we are able to repeatedly observe a pulsar, detecting the times of arrival of its pulsation, and then trying to reconstruct the presence of trends in these times of arrival, trends from a microsecond scale up to decade scale. And why this is important? Because millisecond pulsar especially are wonderful clocks. And so you have a laboratory tools for associating these trends to some physical effect. For example, these trends could represent the possibility of detecting an orbit which the pulsar is following, and all the orbital parameters, the classical orbital parameters, maybe you remember the Kepler laws at the time of the early study, you can really use them for reconstruct all the shape of the orbit. And you can do that with extremely high precision. Look, for example, at this object, this pulsar. On that day, we were able to measure its rotation period with that incredible precision. To my knowledge, please correct me if I'm missing something, there is no field in no science where you can have a measurement, not a theoretical extrapolation of a number, but a measurement of a physical quantity with 6 digits of precision, like we can do in this case. At this point, you can imagine that even a very small variation in this period can be detected and associated to some physical effect. For example, a physical effect predicted by general relativity is the so-called advance of the periastron. The elliptical orbit of two rotating bodies shifts ahead, which is not predicted by the Keplerian law, but it's there in general relativity, and you can detect that. Or, for example, you can detect the fact that the orbit is shrinking. Again, Kepler and Newton, who explained those laws, exclude that two bodies can get approaching to each other along their orbit. General relativity predicts that clearly, and you can try to see if that's true with these wonderful clocks. And other effects, likewise the so-called Shapiro delay, are due to the fact that the radio pulses have to go through the space-time, which is not flat, and being carved, the radio waves take a bit more of time to reach you, and you can detect this effect. And when that was done for the first time is well known. That provided a Nobel Prize in 1993 to Halsey Taylor. But more recently, an even better system, binary system, was discovered, is the so-called double pulsar. Here you can see the precision with which you can measure the rotational period and the orbital period of this system, and also many other general relativity effects have been measured. I have no time for entering detail. I'm just showing you the fact that this is the only, so far, binary system in which we have two radio pulsars, both of them active as radio pulsars. In all the other systems, there is one radio pulsar and a companion star. This is the only case in which we have two of this system, and I'm very happy that my student at that time, Martha Bourget, was the one who discovered again, a female astronomer discovered this system 20 years ago now. Time is passing incredibly. And after having observed this for 20 years, what's the status of the thing? I just show you a comparison with the Nobel Prize system. What you see there is in black the curve predicted by general relativity for the shrinking of the orbit of this system. And the points up there are what the observation showed, and that clearly deserved a perfectly allocated Nobel Prize. And the consequences of that was that the radiative prediction of general relativity were tested at the 0.16% level. Now, with the double pulsar, this is the situation. In red is the prediction, and I can show you in blue the observational points. I always show this to my student and also to general public, because this is one of the very few cases in science in which there is a prediction very precise well before the observations, and the observation goes on the prediction. This is not a fit. The red line is not a fit to the blue point. Is a prediction resulting from other observations, and the blue points are how nature really behaves. And there are other effects related to gravitational wave, to gravitational bending of electromagnetic waves, which have been put in evidence with these long-standing studies. And in particular, these two effects were never seen in any system before. And of course, this is a good confirmation again of the prediction of Albert Einstein's theory. And the second big and last thing which I want to mention is to use this object as gravitational wave detector. So, this is a strange situation, requiring a bit more of thinking. Imagine to have our Earth with the radio telescopes on that and a radio pulsars somewhere in our galaxy, and a gravitational waves source. Gravitational waves are completely different with respect to electromagnetic waves. They are generated when massive objects are in an accelerated motion. And this is a typical representation of two objects in accelerated motion with some gravitational waves emitted. Of course, it's a pictorial representation. The truth is completely different. They are not this kind of surface waves, but pardon myself for using this rough representation. The point is that these gravitational waves perturbs the space-time, and also the space-time where the Earth and the radio pulsar is located. And so the space-time where we are and where the H radio pulsar is start feeling these bypassing gravitational waves. And so if you measure the times of arrival of the pulsation from the radio pulsar to the Earth, when the gravitational waves passes by, you have to perceive this kind of variation in the times of arrival, which cannot be ascribed to the specific pulsar or to the Earth, but to something else. And you can also have a simple rule for estimating how great the effect can be. The typical gravitational wave quantity in observations is the so-called gravitational wave strain, which is the H number there. And if you calculate the ratio among the precision sigma TOA with which you can determine the time of arrival of a pulse, divided by the time span you observe that pulsar, you can see that the strain measurable is in the range of the feasibility. For the precision, sigma TOA can be of order 10 nanosecond, and the time scale in the denominator there can be 30 years. At that point, you reach the level of precision for hoping to detect something. Of course, when you have only one pulsar, you can never be sure that something else didn't happen. You need many of them and see this breadth for all of them. At that point, you can be relatively sure that what is going on is bypassing gravitational waves. And so you need a pulsar timing array. Many, 20 and more, millisecond pulsar distributed in the sky to be looked at every couple of weeks typically, and see if you can detect for all of them simultaneously this signal. And this is what has been done nowadays since 30 years by three groups in the world at the moment. And the underlying idea is that the universe is filled with the gravitational waves produced many, many billions of years ago by the orbiting of two supermassive black holes. We now assume that supermassive black holes are located at the center of most, if not all, of the galaxies. And sometimes these galaxies merge, and their gravitational and their supermassive black hole in the end will merge again. But while they are spiraling, they emit gravitational waves, and you can predict, this is basically a picture of this, that when they are close enough for reducing their orbital size due to emission of gravitational waves, they emit these waves. This is a picture of the space-time with that green grid and the two supermassive black holes spiraling, one closest to the other progressively and emitting gravitational waves, which perturbs the space-time and so perturbs the times of arrival of the radio pulsars, which you can detect with the radio telescope. And I was saying that this typical effect has a frequency of about 3, 5, 10 nanohertz. So they are very long gravitational waves, 10 years long in period, which nicely complement the gravitational waves already discovered, which have been discovered by the interferometers on the ground, likewise LIGO and Virgo. They have much faster period of order several hertz or kilohertz. So they are gravitational waves emitted by much smaller rotating, orbiting bodies, and so their typical period is 1 millisecond to 1/10 of second. Here we are discussing about 10 of years gravitational waves. And I'm a member of the European Consortium for finding these gravitational waves, which is called the EPTA, European Pulsar Timing Array, based on 5 radio telescopes, one of them in Sardinia, which INAF is the leader of. And of course, there are other groups in the world. This is the full plan. Nowadays, unfortunately, Arecibo is not available anymore since it collapsed, but all the others are still active and looking at this ensemble of targets to try to finally detect a signal. And what's the status of the things now? We have, after 20 years, seen that there is a common breadth across all the pulsar. What we call is a very technical word, so I don't want to enter too much in detail, an uncorrelated red noise signal. And so, and this is very promising because in any perspective that you can have for arriving to the real detection of these gravitational waves, the first thing that you'll see is this common signal. But you need a bit more. You need to see that this common signal is correlated in a proper way across the various pulsars for being sure that this signal is really a gravitational wave signal. And we will be happy when the orange line there will be followed by the data point, which are the black points with the error bars. You see that this is a paper of past year. We are not yet there. There is yet not a statistically significant correspondence among the black points and the orange line, but that is what we are nowadays looking for, and hopefully very soon we might start seeing if those black points will distribute along the orange line. And more to come. The future perspective will be mostly supported by this wonderful new experiment, which will be built in 2 continents, but where Italy is one of the main actors, called SKO, Square Kilometer Array Observatory. For example, that will allow to overcome 12,000 pulsars known, among which there will be many exotic systems, including the long-sought pulsar black hole system. It will allow to detect times of arrival with 10 times better precision, going from 10 nanosecond to some nanosecond precision, which will improve all the gravitational tests. And also the timing arrays, instead of having some tens of useful pulsars, will have some hundreds of useful pulsars. And so we really think we will be able to start gravitational wave, long period gravitational wave astronomy. And among the interesting new system which we might hope to discover, there are these cartoons showing some very exotic possible system, likewise, for example, a tripole pulsar system, and they will be really exceptional system for doing a lot of things. Last slide about a pulsar black hole, already mentioned by Marco, what we could do with the pulsar black hole system. If the black hole will be a stellar mass black hole, so some tens of solar massives, we will be able to measure the mass of the system at better than 0.1%, but also the spin of the black hole at better than 1%. And combining these 2 information, we will be able to check if this conjecture produced by Penrose, Nobel Prize 2 years ago, thanks to this, about the fact that there are no naked singularities in the universe. What that means? When you have a black hole, if you follow the idea of a black hole, you go towards a point of infinite density at the center of that, which is, of course, not feasible in a meaningful way in physics. So the great idea is that sometimes when a black hole produces, a horizon surrounds that and prevents you to look into the singularity. Basically, the singularity is outside the physical world, which you can test. And so the prediction of Penrose is that all the singularities in the universe must have a dress, must have been protected by this horizon. And you can directly test that, since the combination of those numbers must be below 1, if that's true. And with SKO, we will be able to do that. The second very famous prediction about a black hole is the fact that the black hole has no airs. basically the prediction is that a black hole can be completely defined only by its charge, electrical charge, but that's typically 0, its mass and its spin. No other features can be attributed to a black hole. If that is true, the combination of those numbers, in particular the quantity Q, must be exactly equal to the opposite of the square of the quantity psi mentioned above. So we can do tests measuring those quantities directly of this theorem, which stems from general relativity. As you can see, Jocelyn left a huge amount of possibility to science. We must be really grateful to them, to her forever. And also on a personal side, again, thanks a lot for having let me to live a scientific life, very, very fun. Thank you.
Thank you very much, Andrea, for this enlightening talk. And I'm sure there are a few questions, so we have time for a couple of questions if anybody's interested. Marco.
I cannot resist. You showed this triple system with 3 millisecond pulsars. Let's think of something with 2 millisecond pulsars, because how can they be formed? 2 millisecond pulsars.
They can be found in globular clusters, since this very crowded stellar environment allows for stars to meet each other, which is basically impossible for our sun. The closest star is 4 light years away, so no chance of having some encounter. But inside this system, stars can chat to each other very frequently, exchange companions, and since we already know that there are double neutron star systems in this globular cluster and a lot of millisecond pulsar, why not thinking that in one of these encounters a third neutron star could join the other two and produce a triple system?
Any other question? Yes, please, Alessandra.
Thank you very much for this nice presentation. I cannot resist as well to make a question, because I working in celestial mechanics, so within the solar system, not far as pulsars. But I wonder if there is any evidence of spin-orbit coupling in such systems, and precisely resonances, and possibly also in the only example where you have a binary pulsar, if there is a synchronization between the two pulsars.
Three very interesting questions. About resonances, if you are meaning orbital resonances, the answer is yes. In the system which I mentioned before, where the first extrasolar planets were discovered, the 3 planets discovered there are just in a typical orbital resonance. As far as precession and spin-orbit coupling, yes, again, in the double pulsar, we have detected the precession of the spin axis of one of the 2 pulsars with respect to the other, and the prediction of general relativity about the precessional rate agrees nicely, also in this case, with our measurement of the precession rate. Now I don't remember anymore the third question, sorry.
No, this is fine, but is there tidal friction?
Okay, about the synchronization, again, the answer is yes, but not for the double neutron star system. The 2 neutron stars are too compact and too stiff for allowing tidal effect to synchronize them. And so their rotational speed are different. But in system where we have a neutron star, a radio pulsar, and a white dwarf, which is a compact system, but not so compact, and so tides can be affected. In some of this system, we see that the rotational pace of the white dwarf is at the same rhythm of the orbital period, and so they synchronized effectively.
One very last question.
It's a let's stay tuned. I cannot say any more at this point. Yes, there are improvements. Yes.
Okay, so thank you again, and let's see. Let's thank again Andrea Possenti, and
Thank you all, and thanks Jocelyn first of all.
and now we have a presentation from Niccolò Bucciantini about the nature of pulsars and neutron stars.
So let me thank the organizer for inviting me here. I had the pleasure of meeting Professor Bell a long time ago, I think in Montreal, celebrating the 40 year of the discovery of pulsars. And I'm so proud to be here again for her. And I thank Andrea, who already showed you what kind of extraordinary machine this object can be. And I will try to show you how these objects are important, even beyond what you can naively think as the realm of astrophysics. Because these objects are really pervade many aspects of modern physics today, and they are important in so many different fields that they are kind of a special lab where we can investigate this process where we don't know actually in high details. So this is a brief pictures of the physical cosmos that surrounds a pulsar. All this piece of physics from general relativity, Andrea told you about how pulsar can be used to actually test the properties of space-times, all the way to nuclear physics, particle physics, stellar physics, condensed matter. All of these find its way in this beautiful object. And if you are a physicist, you can find your domain in a certain spot of neutron star, outside or inside, depends on you. So I will start with nuclear physics. So what happens deep in the interior of a pulsar and a neutron star? And I will begin by saying that the very existence of pulsar is the testimony of an incredibly subtle effect of nuclear physics. So the force that keeps nuclei together, that bounds protons and electrons, at the scale of the nuclei is an attractive force. You have to take particles and pull them together. Yet, at a scale which is much smaller than the size of an atomic nucleus, at a scale which is about 1/10 of the size of a protons, this special force becomes repulsive and prevent the particle from coming too close to one another. Now, you can imagine that the force that acts on a scale which is 1/10 of the radius of a protons, 1/millionth of a billionth of a millimeters, would be of little relevance to the macroscopic world where we live. Yes, it somehow regulates how nuclei behaves, but that sits so far away from our chairs or our rocks or our planets. And yet, if it wasn't for this very repulsive core, what is called the repulsive core, the hard core of the nuclear force, pulsar would just not exist. So an object 10 kilometers in size is the testimony of the property of a force that only acts on a scale which is billions of times smaller. And it took nuclear physicists some time to realize the presence of these repulsive natures in the interaction between nucleons. Before, it wasn't so obvious. And you can think of it like an object of 10 kilometer size, the size of Rome, depends on it. So this already illustrates you how exceptional these objects are. So this is a brief pictures of our understanding of the way I think we understand the constituents of matters. Now, matters is done by small building blocks, particles, electrons, neutrinos, and then there are the massive ones that are called quarks. Quarks are the constituents of our nucleons. Protons and neutrons are not the fundamental building block of matters, but they're formed of quarks. And quarks lives inside neutrons and protons. They bind together through the nuclear force by exchanging particles that are called gluons. And the image that you see on top is a naive description of what a nucleon is. 3 quarks that exchange gluons. But we came to realize that the physics inside this particle is far more complex than this. And the reason is that the nuclear force, the strong force that binds quarks, is a highly nonlinear. So quarks interact among themselves with gluons, and gluons interact among themselves with other gluons and with other quarks, and it is a mess to figure out how those together. So this is a pictures of this is the naive picture. This is a less naive pictures of the same particle seen inside. Now, in order to figure out the complexity of the strong force, which is one of the basic forces that regulates natures, you have to figure out how particles interact. And one way we have to do that, the only way actually we have to do it, is to take 2 protons or 2 particles and smash one against the other, break them into their basic constituents, the quark, and then see how the quark reacts. And this is what we do in particle accelerator. We take this particle, we accelerate them, we smash one against the other, they break apart, they form other particles, they spawn different species that decay, are unstable, and by looking at how long they survive, what they do, what is their mass, we try to reconstruct this interaction, which is otherwise inaccessible to us. But unfortunately, this is not enough to really understand the behavior of this force. And the reason is that when we do this, when we smash particle in our accelerator, we're actually looking at what we call a high temperature, low density regime. So basically, we only can test what happens when 2 particles smash against each other. But this is a nonlinear force. So the interaction between 2 particles depends if there are also nearby particles around them. And nuclei are not just made of 2 particles, they're made of many particles. If we want to understand how matter works, the basic constituent of our world, we have to understand how they behave when there are many particles together, packed together. Our accelerator don't allow us to really do that. They only allow us to sample different regime, much closer to the Big Bang. So we need to go what is called the high density, low temperature regime. Many particles close together. But the point is that it's very difficult to pack particles close together. We don't know how to do that. We can only have nuclei available, but the universe knows how to do it. And it does it inside the core of neutron stars. There, the density is so high and the pressure is so high that you can take matter and push it in conditions that cannot be reached in our lab. So this is the way we test this highly nonlinear regime, and we test these many body interactions. And it has a name, the study of these in nuclear physics. This is called the holy grail of nuclear physics, because we really don't know what is inside. We cannot go on a neutron stars and dig down and take a piece of its core and look at it and see how it's done. So we have, in a certain sense, to do a quest for it. So this is the basic pictures of the structure of a neutron star. You have a crust outside, which is made of, let's call it regular matter, or something that at least we think we understand how it works. We have an intermediate regions made of regular nucleons, and then there is the core. And that is where our theoretical models fails. Well, we have no idea what's happening there. There's the famous Ixunt Leones of the map that people used to write when in the middle of Africa, because they have absolutely no idea what was behind. And we have plenty of models for this. Every theoretical basic physical theory make a prediction. And this prediction turns out to change the structure of a neutron star. Some theory predicts that we will have just regular nucleons. That make neutron star very stiff, rigid. Other theory predict the appearance of new particles, and that makes neutron star soft, not really soft the way we mean it, but soft. And all of these means that the stars will have a different shape. So measuring the shape of the stars, larger or smaller, will ultimately tell you what are the conditions in the core of a neutron star. A stiff star will actually be bigger. A soft star will be more compressible and as such a bit smaller. No, it's not that easy. To give you an idea, a neutron star is the size of a neurocent placed on the surface of the planet Pluto. That's the kind of angular size of an object. We have to look at something like that and figure out if it's actually an eurocent or 2 eurocent on the surface of Pluto. That's the kind of measure that we need to do. So what you can see here is a set of curves that describes various physical ideas of the behavior of matter and how they translate into the so-called mass-radius relation of neutron stars. So given a certain mass, how big will be my neutron stars? So the trick here is to measure both mass and radii. Now, we can already do something just by measuring the mass, because you see some horizontal line that sits on top. Those are measured the mass of neutron star in binary systems, where you can do the measure that Andrea was talking about. And of course, your theory must be good enough at least to reach that mass. If you predict that your maximum in your model is, I don't know, 1.5, and you measure 2, well, your model is wrong, of course. It doesn't have a maximum all the way. So that already helped us remove lots and lots of theoretical models that were pushed forward in the past. Now, how do we do this? Well, there are various ways that we have developed in the past. I will discuss one, which is based on an instrument that we have built that's called NICER. Is the Neutron Star Internal Composition Explorer. It's an object that lives, it's an instrument that lives on the space station. And its aim is to measure the mass and radii, actually the compactness, the ratio, the mass of the radius of neutron stars, those eurocents at the distance of Pluto, essentially. And it does it on a very clever way. It's not easy. I'm trivializing the picture for you, but these objects are general relativistic objects. They bend their space-time around. So in practice, light doesn't travel straight. And as a consequence, you can see beyond the horizon. So for us, you cannot see beyond the horizon because your line of sight goes straight. It hits the horizon, and that's fine. But light bends in this close to the neutron stars. So basically, when we look at the neutron stars, we see not just the face of the 2 eurocents, we see a little bit also on the back. So it will be like staring at the other side of the moon. And this property changes the way the light coming from the neutron stars reach us. So there are a certain set of neutron stars that have a hot spot on their surface, hot region. And as they rotate, the regions is sometimes in front of you and sometimes is on the back. When it is in front of you, it radiates light, and the light coming from the neutron star is larger. When it's on the back, you can't see it, and of course, the light is smaller. But as I told you, given that you can see beyond the horizon, chances that you will be able to see a little bit of that light, even when the hot spot is on the back. Now, understanding how much light that hot spot on the back send to you will give you an idea of how much you can see beyond the horizon. And that will tell you how compact the object is, how strong the light bending is. We are technically doing what Eddington did when he tried to measure the deflection of light close to the surface of the sun. We are using essentially the same physics here in a slightly different approach. And we have been able to put some numbers or to put some constraint on the diagram that I've shown you before. Of course, these are astrophysical constraints. You have to take them. In astrophysics, there is no exact numbers, because unfortunately, we don't have a lab where we can put things under control. We have to look at the universe, and the universe gave us information, but it doesn't allow us to go there and regulate things the way we would like them. So these are the results of 2 measures done by the NICER observatory, the pink and blue spots. And they tell you essentially that only those curves that pass within those regions represent a theory that today are possible. Every other line that do not pass through those regions, you can throw out. So this is the way we actually try to understand how matter works. In a realm that has almost nothing to do with normal astronomy or stars or other things, and this is where nuclear physics sits. Now, this is for the interior. Now I'm gonna tell you another things about the exterior of neutron stars, of course, and before going there, however, I would like to point to you that even those part of the neutron stars that were kind of regular, the one I told you, oh, here is the crust, and we know how it works, and here is the nuclear phase, and we know how it works. We really don't know how it works exactly. There is a region just underneath the crust of a neutron star that got a very funny name. It's called the pasta phase. And it's called the pasta phase, yes, and this is a good pasta, because Now, matters, the nuclei acquires very funny shapes. Now, if you look at your textbook, nuclei are small sphere that sits at the center of atoms. And they are small sphere-like object in our experimental worlds. But at those density, nuclei change shape. Sometimes they become very, very long, and these are called spaghetti. Sometimes they form layers, sheets, and those are called lasagne. Sometimes they form blobs, and those are called gnocchi. And sometimes they form structure with the holes, and those are called pancakes. And if you think of it, now it seems funny, but these indicates peculiar properties, depends on the properties of the force that keeps the nuclei together, the kind of shape that you have, if you can have a certain shape or other. They do affect the way neutron star behaves. They do affect the way neutron star radiates their energy, the way they cool down, the way the magnetic field evolve in neutron stars depend on the structural property. So if you can think of it, even the regular part of neutron star, the one closest to our worlds, have properties that are very, very far removed for our common understanding of things. So what happened outside? Well, outside we are in a realm that's, let's say, a bit more to our understanding. So as Andrea told you, basically, neutron stars are big rotating magnets. You can think of it. And big rotating magnets produce energy, and we know why, because basically we have been using rotating magnet to produce energy for about 200 years, thanks to Mr. Faraday. Mr. Faraday invented that Faraday disk that sits there, and you can find in any science history museums, basically. It's an object that you turn your wheel, it spins up, and you light the bulb. And for those of us who was born before LED lights, you remember that on our bike there was a dynamo. You will plug it, the dynamo will rotate, and the bulb on front will turn on. So this is exactly what neutron stars do. They are rotating, big rotating magnet, and the combination of the rotation and the magnetic field makes them excellent electric engine. They produce far more energy than our bike. And if you remember well, the amount of light you were able to produce would depend on how fast you were actually biking. So if you were going slowly, the light will be dim. If you were going fast, the light will be bright. For pulsar, it's more or less the same. If they spin fast, they have lots and lots of energy and lots of potential energy, and they're good and active object. As they slow down, they become weaker object, and at a certain point, they will finally die. They will not be strong enough anymore. Now, what happened is that because of this interplay of the magnetic field and the rotations, they become source of light in the darkness. They turn on in the same as a regular light. And the reason is quite simple. Basically, the electric field that you create with this rotation and magnetic field is so strong that instead of turning your bulb on, it can extract electrons from the surface of the neutron star. It can pull them out and accelerate to very high energy. And it does this along the field line of the magnetic field. So basically, you are, instead of your regular battery that moves electron through the wire, this really pulls electron out in space. These electrons go very, very fast, and they move along this magnetic field line. It's in curved trajectory. And when charge moves in curved trajectory, they produce light. It's a special kind of light. It's called synchrotron radiation or curvature radiation. We do this in our lab. There is a synchrotron at Trieste, which is a machine that does exactly that. It takes electrons, accelerates them. These electrons move in a circle and produce light. It's a very special kind of light. We can see it. And pulsar and the region surrounding pulsar were the first place in the sky, in the universe, where this form of light was actually recognized about 40 years ago. And this is the synchrotron light. And when we look at pulsar in radio or in other wavelength, the beam, the radiation that we see, we think originates from this curvature or synchrotron lights that is produced by this high energy electron as they get pulled out of the system. So this explains why we do see radiation. We are able basically to turn our small dynamo on our bike that will move electron through the simple wire into something that is a cannon of electrons that fires them in the sky, in the universe. And as they are fired out, they emit light in the magnetic field. There is another interesting thing that happens to those particles as they move, and those electrons and those light. As it moves, outside of the neutron stars. Now, if you remember your old class of physics too, light is a solution of Maxwell equation. Maxwell equation describes electromagnetic field. They're beautiful equations, and they are easy. Now, my student would strongly disagree on that statement, but in general, for me, they are easy, because easy means that they are linear equations. And linear equation for us physicists has a profound existential meaning. It means that the entity described by those equations are independent of each other. So what are the entities described by Maxwell equations? Those are the photons, the particle of light. And the fact that Maxwell equations are linear tells me that each photon lives like a monad in its own world, without caring anything of the fact that there are nearby photons. Photons don't interact with each other. They are independent solution of Maxwell equation. 1 photons, 2 photons, 1 billion photons, they can all live together like if they were alone in the universe. But this is classical physics. And there are more things in Earth and Sky than in your book of philosophy or in your philosophy dreams. And the world, it's far more complex than even Maxwell equation would describe. The deep worlds, the fine worlds of our reality is pervaded by so-called vacuum particle, virtual particle. So there is not really a vacuum. There are small pairs of particles that are born and then they die continuously, and they fill this vacuum. And the interesting thing is that photons, real photons, one of the solutions of Maxwell equation, can actually interact with those virtual particles. Now, because they exist for a very brief time, for incredibly short times, one of these photons can turn into a virtual pair of particles. And then those virtual pair of particles, what they can do? Well, typically they die, they annihilate with each other, and they recreate the photons they begin with. So actually, this is like changing for a brief time its natures. But during those brief times where this virtual particle exists, there is a very, very tiny chance that this virtual particle can interact with another photons or with another electromagnetic field. Now, what happens is that if you interact with another field and you are able to get enough energy to upgrade yourself to a real particle, then you are done. You get out of the vacuum and you become real. And your original photons, it's gone. It's turned one of these virtual pair into a real pair. Of course, it's not a process that happens so easily, right? Because this particle lives a very, very short times, and so all of these have to happen in this macroscopic times at the edge of quantum mechanics ability to resolve time, but it happens. And in the magnetosphere, in this space surrounding the pulsar, the magnetic field is so strong that basically as the photon propagates, during the brief time they materialize as an independent pair, they can interact with the magnetic field surrounding it, and that pair becomes real. And now you have created the matter out of light. That's what happened. The light that comes from the surface, the light produced by those electrons pulled out of the surface, turn into matter. Actually, it turns into a strange form of matter, because when you create particle, you create always a pair particle-antiparticle. So you create electrons and positrons, always in pairs. And of course, these electrons and positrons find themselves in this enormous magnetic field and electric field of this spinning magnet, and they repeat. They are reaccelerated, they re-emit light, and this light, again, has a small chance of creating another pair of particles. And you get basically what is called as a pair cascade. Out of a single particle, you will create many, many more. Actually, you create 1 million particles for each one that you typically pull out of the surface. And all of these ends up into forming a winds of particles that travel through the space. And as it travels through the space, it produces, on one hand, the radiation that you observe, those beams of radiation that flows in our direction and that gives you the pulsed signal. But it also forms true winds, like the wind that we have on Earth. And this wind blows and forms what is called as a wind bubble. Now, we don't see the wind from this object. It's very difficult to see the winds from this object because it's cold, essentially. and it's highly relativistic, which means that radiation is beamed away from us. But we can see where these winds interact with the environment. And when we look at the environment around pulsar, especially the young one, that's what we see. We see an environment that's populated with these electron and positrons that fills the entire system. This is the Crab Nebula. What you see here is the radiation from the particle created at the base of my pulsar itself. And as I say, half of these particles are antimatter particles. And they are important because it's not very easy to create antimatter in the universe. There are not that many ways. Cosmic ray can make antimatter, but cosmic ray are highly constrained. We know, big word for physics, but we know that they are subject to certain constraints, and the amount of antimatter that they can produce is not enough to explain what we observe. Pulsar can produce a lot of antimatter. And why do we care of this? Because another way of producing antimatter is through the decay of dark matter. And when you look for the decay of dark matter, you look for gamma ray radiation that comes out of this positron that dies. The problem is that typically where you look for antimatter, it's the center of galaxy, but that's also a place where you have plenty of pulsar, which means that you have to be very careful in understanding what is the role of pulsar in order to understand if what you are seeing has this what many physicists would call a more mundane origin of the pulsar, because at least we know they exist, instead of dark matter, which is less mundane because we don't even know if it exists to begin with. We know that this particle can be accelerated to incredibly high energy. This is an experiment to measure high energy particle that sits essentially on top of the Tibet high plane. And we know that this object that we like the Crab Nebula that we observe indeed produce high energy radiations. Now, the Crab Nebula, we also know that originated from a supernova. We know this supernova, we even know the date exploded because we have Chinese records that point us to the exact date. This was the 4th of July of 1054. And that's what we see today. We see the object expanding. So we have a beautiful connection between pulsars, explosions, nebulae. We do see the pulsar at the center because it actually shines in optical light in this case, so we can actually put our optical telescope and see the things clicking, and we can also listen to it. And I hope it works. This is the Crab Nebula. This is if you take a radio telescope and you put your heat cuff and your earplug and you listen to it, that's what you will listen. 33 beats per second. That's the rotations. And so why they are important? Because these are our garden variety of high physics laboratory. So you can study there all the high physics with X-ray that you can essentially do to investigate physical systems that are far away from us and we cannot really look in such a beautiful detail like this. I will conclude with the last slides. I will take some extra time to show you that pulsar matters not just for science, but, well, even for science, but also for somebody else. So this is the plate of the Pioneer Voyager, I can't remember now, satellite. This is one of the satellites launched in the 70s, and it was a satellite designed to escape the solar system. So the scientists and technicians working on it had this beautiful idea. What happened if an alien civilization managed to recover it somewhere else in the universe? So we will put a plate on it to tell who made it and our address. And so you have to tell aliens the address of the Earth, right? It's already a mess when I have to tell the address where I live to my friends. So imagine telling an alien which doesn't speak your language, I have absolutely no idea what your language might even be, how to find the Earth. Now, there are some things that are obvious in the plate. For example, men and women, the way we are done, the size of the satellite. There is a solar system design on the bottom. And then there is this starry diagram there. The starry diagram is the address of the Earth. And it's the address of the Earth because at the end of which one of those rays sits a pulsar. And those bars that you see are a way of telling which pulsar is. Now you remember the lighthouse effect. If you have ever taken a boat and ever looked at a sea chart, you will see that lighthouses are all marked with a specific period. So when you navigate at night, just by looking how frequently a lighthouse blink, you can tell which port is there or where you are on the map. And we are doing exactly the same. We are telling the aliens, look, there are pulsars all around us. Those pulsars have a specific blinking period. And so if you triangulate all your blinking periods, you know that here 3 times a second, like 10 times per second, here 20 times per second, and you put it at the very center of all the triangulation sits small planets with perhaps still someone there to greet you. And with this, I will just conclude. Thank you very much.
Thank you very much. And we have time for 1 or 2 questions, please. Well, I work in a field which is really far from this, so I was a bit astonished by the possibility to investigate the interior of a neutron star. And so the question is a naive one. How many different models do you have, and how close are we to select the right one or the several right ones?
Model plenty. It's a small, plenty is a small number. So the point is that there are an enormous variety of models. So the problem is that it's the nuclear force, the strong force, is so complex in its all details, that we don't really know many of the parameters that enter into the model. So globally speaking, I will tell you that you can divide them into 4 big groups. One is regular matter, that tells you that basically the interior of a neutron star is not that different from atomic nuclei, all the way down. You get neutrons, protons, and something in between. There are so-called condensed model, where you have pions and kaons, or other particles that materialize in the interior of a neutron star. Many of these models have been rejected because they make the neutron star very soft and they do not reach a very high mass. Then you have a model of the confined quark. Pressure gets so high that basically you can break the particle into its basic constituent and you have a soup of quark. Those kind of make the neutron star a bit more stiff and they're still viable. And you have even models with strange matter. So where you materialize a particle containing the strange quark, which is a quark that doesn't exist in normal matter because it will spontaneously decay down, but those density can be materialized. Now, the big problem is that you can never see a quark in isolations. So quarks always manifest themselves into couple. As a result of this, you cannot measure the mass of a single quark, because when they are born into a couple, the interaction energy matters a lot. So as a result, no one knows what is the mass of the strange quark. There are some estimates, but no one knows. And it all depends on the mass of the strange quark, if you can have or not have the strange quark. So being able, for example, to nail down to a strange equation of state, for example, would be able to tell us what is the mass of the strange quark, which is one of the fundamental quantities we can't actually measure. I must also say that theorists are very clever. So that's a good point for theorists, which means that our astronomical measures are not kind of point that nails things down, but are big error bar regions. And theorists are always good enough to have their model fit inside. I mean, if you tell, well, this model was not really correct, yeah, but I might change this parameter and I can push it up or down or make it stick there. So we will have to make many, many measurements in order to have a really, really good understanding or to nail down. But at least we can remove the several of the old theory, the one that have all masses below 2 solar masses, which is the current mass 2.08 is the current best estimate.
Thank you very much. Any other question? Marco.
Nico, I have a difficult question for you. So the August 17th, 2017, there were these 2 neutron stars which coalesced and produced the gravitational wave event. It's the only one which actually produced an electromagnetic signal afterwards. So we have 2 neutron stars, 1.4, 1.5 solar masses, which merge. What happens next? So what do they form? Did they form a super neutron star or a mini black hole?
So we have 2 problems there. One is that our instrument was good enough to see them merging, but not all the way down. And because the neutron star are a small object, so basically when they merge, they spin so fast that that very final phase of the merger went out of the observing windows of LIGO. So we have missed the merging phase, and we have seen nothing else. We have seen no ring down of another object, and in the electromagnetic signal there is no evidence for the survival of some supermassive remnant. So basically the problem is that the equational state will also tell you how high you can go in mass. So when you merge two stars, if your equational state is allow you to have a very big object, they might survive. You might create a super neutron star or what is called an hypermassive neutron star. We haven't seen trace of that in that event. But we have other short gamma ray bars when we do see emission at later times that normally we think originates from one of these events. We will have to go a bit higher in frequency in order to actually sample that, because I believe that the frequency window is about 700 Hertz for LIGO, something like that, to about 1 kilohertz. And in the frequency that you expect for the merger is a bit higher than that. So, and the sensitivity goes up again. So we are really missing that moment of touch and merger that we would like to have it. So, but we could do something ahead by looking at the tidal deformation of the star. So there are some constraints, because even there, when you merge, you can stretch the neutron star. There you can get some idea of their mass-radius relation. But again, those are big region on that mass-radius diagram, still big region on that mass-radius diagrams. So astronomers work with statistics. Typically, one event is not enough for us to tell we are there. We need many, many more. Then statistics accumulates, you can kind of nail down things where they should be.
So let's thank Nicolò again, and having seen how far we got with pulsar neutron stars, it's now time to welcome Jocelyn Bell-Bournel for her talk in this event. Please welcome Jocelyn. Sure.
So thank you very much to the Academy for many kindnesses, and thank you to the previous speakers for their setting the scene so very thoroughly, which has made my job a good deal more easy. I was a graduate student in Cambridge when pulsars were discovered, and so this is, well, I'm still there as a graduate student in Cambridge. I'm going to say a little bit about my background, then I'm going to tell the story of the discovery of pulsars. One of the delights of having had that experience is every so often somebody comes to me and says, you know, I nearly discovered pulsars, and tells me the story. And those stories are as revealing as the discovery story itself. So I will relate some of those, though rather more briefly, and look at what I think were some of the major factors that led to the discovery when it happened, where it happened. So, as you've been already told, I started life in the north of Ireland. Not a very happy part of the British Isles, great friction between Protestant community, Catholic community, politics and religion completely intertwined, and the two communities living separately. My family is actually Quaker, and we tried to straddle the divide, which sometimes meant you got shot at by both sides. I failed my first important public exam at age 11, but because it had always been my parents' intention that I would have some of my schooling out of Northern Ireland, away from the Protestant Catholic conflict. The head teacher allowed me to continue in the academic stream. I remember the excitement of moving into senior school, you know, different teachers, different subjects. You're not sat in the one room with the one teacher all the time. Whoops. Okay. Right. We had an important exam at age 11, which I failed. It was supposed to distinguish between whether you were academic or not, but parents pressurized the school and I was allowed into the academic stream because I was going away to school in England. It was interesting entering senior school, lots of different subjects, lots of different teachers, much more interesting than the primary schooling. But I remember on the Wednesday of the first week of the first term, a message goes around the first year class. This afternoon, boys to that place, girls to that place. And I thought, that's because of sport. Boys sport, girls sport. It wasn't. That was the science laboratory. That was the cookery room. No choice, no discussion. I was upset. My parents had said I'd get to do science. I tried protesting to the cookery teacher, but no. But when I got home that night and told my parents, they were woof, and they phoned the head teacher. I think they maybe phoned some other people as well. The local doctor had a daughter in the class. He phoned the head teacher. And some relatives of theirs phoned the head teacher. And the next time the science class met, there were 3 girls, 3 of us, and all the boys. And clearly we were dynamite. If that is the teacher's desk, we had to sit here. No trouble from us. We did physics the first term. I loved it. It was easy. I came top in the exam, but I made an interesting error. One question was, what is the speed of light? We worked in old British units. I wrote down 186,000 miles per second, which is the right answer in those units. And then for the first time in my life, looked at that answer and thought, that's very big, and changed miles per second to miles per hour. So I only got 97%. We did chemistry the next term. That was okay. Third term, we did biology. Here is a flower. Draw the flower, label the parts, learn the names. You've done that. Good. Here's another flower. Draw the flower, label the whole term was drawing flowers and identifying their parts. And I thought, boring, and had a prejudice against biology ever since. And okay, right. So ultimately, I went away to school in England, a girls' boarding school, Quaker girls' boarding school. Girls' schools had trouble getting good science teachers. I remember our chemistry teacher standing at the front, great big picture of the periodic table up behind him. And we asked him a question about why, let's say, hydrogen and oxygen combine in the way they do to make water. And he should have told us about electronic structure and the periodic table. I don't think he knew what that was. He said, God made it so. And at a church school. So girls' schools had problems getting good science teachers, but our physics teacher was brilliant. He was very old. He had already retired twice and come back to teach us, but he was very good and very clear. And I focused on maths and physics and did that right up to school leaving level. I had become interested in astronomy. Then an astronomer pointed out, you know, we work at night. I thought, oh, I need my sleep. I can't be an astronomer. And then I got to hear about astronomy at other wavelengths, particularly radio astronomy, which was the emerging subject then. And I thought, right, I will be a radio astronomer, but I will do a physics degree first, not an astronomy degree, because that's all optical astronomy. I will do a physics degree first, and if I cannot be an astronomer, there are plenty of other things I can do with a physics degree. I ended up the only woman in the class, 49 men and me. And in Glasgow at that time, when women entered the lecture theatre, the men whistled, catcalled, banged their desks, stamped, big wooden lecture theatres, lots of noise. And the women used to gather outside and enter in a group all at once. But as the only woman, I had no group. And I had to learn to control my blushing, because if you blushed, they just made more noise. And you didn't really have anybody to work with. None of the men would work with the woman. They'd work with each other. So it was a little bit tough. But I survived. I more than survived. And in my final year, we were assigned in groups of 3 or 4 to one of the staff, who was our tutor. And my tutor was a funny little round man called Ron Drever. We'd 3 of us would agree before we went in, look, we're having trouble with the solid state physics course. Let's see if Professor Drever can help us. We'd go in and we say, Professor Drever, da, 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 da. No, I don't understand solid state physics either. Let's talk about the Hanbury, Brown and Twiss interferometer. Or let's talk about this, or let's talk about that. And it became clear to me that Drever's interests were cosmic, if not astronomy per se, at least cosmic. And I made a mental note to watch whatever field he worked in subsequently. And as some of you will know, he became one of the pioneers of gravitational radiation and worked in that field. He died shortly before the Nobel Prize was awarded, if my timing is right. But so he had quite a large influence on me. But having discovered that you did radio astronomy in the daytime, I opted for radio astronomy, applied to go to Jodrell Bank. They never answered. Somebody had said they wouldn't take a woman. Apparently they once had a woman, and that woman and one of the men put the dormitory accommodation to a use for which it wasn't intended. Professor Lovell got to hear about it and said, no more women. Interesting which sex bears the brunt of these mutual encounters. So Jodrell didn't reply, and I thought, well, I'm not going to get into Cambridge. I'm going to have to go to Australia. But the academic year in Australia doesn't begin till January, February. I have some months. I'll put an application into Cambridge anyway, just in case. And very much to my surprise, ended up in Cambridge. That was scary. I don't know how well an earlier Prime Minister, Boris Johnson, is known here. Do you know the kind of character he is? Cambridge was full of young men like Boris. Bags of self-confidence, absolute right to be here. I'm brilliant, nobody can tell me otherwise. And I turn up, and I've come from the north and west of the country. I've got a funny accent, I'm not English, I've not been at a public school, and they're all terribly brilliant and very keen that you know they're brilliant. Well, they have made a mistake admitting me. They are going to discover their mistake and throw me out. But until they throw me out, I'll do my very best so that when they throw me out, I'll know that I haven't wasted the opportunity and I just was not clever enough for Cambridge. So, map of the British Isles. I'm sure you know this. Pointer's not showing very well on the screen. I started in Northern Ireland at number 1. I was at school at number 2. I was in university in Glasgow in number 3. This is all the north and west of the country, the mountainous bit, the heathen bit. The proper stuff is away down south. So when I turn up in Cambridge, I feel very much an outsider, partly because there's so few women, and partly because I'm not from the south of England and I'm not a man. Discomfort or anxiety increased my first day as a radio astronomy graduate student. We each get given a set of tools. These are my tools. I still have them. These are not microelectronics tools. These are full-size wire working tools, because I'm going to be doing full-size wire working kind of stuff. I'm going to spend the first 2 years helping build a radio telescope. Parameters of the radio telescope are here below. 81.5 megahertz antenna, 2,000 dipoles, over 1,000 wooden posts, 200 kilometers of wire and cable, and it covers an area of 57 tennis courts. It's big. My particular job is all the cabling and all the connectors. And in this particular slide, we're checking that the connectors are good. It's low loss cable. You cannot coil it up and take it indoors. So I spend a Cambridge winter working in this little red and white hut and that little red and white hut, putting the plugs and sockets on this end and the far end of these low loss cables. We're using a slotted waveguide to check the impedance. Working literally in the field is surprisingly difficult. For example, it's difficult to solder because the wind cools the soldering iron, and there's damp around and you're dealing with the electricity in damp conditions. It's a little tricky. So there were 6 of us that built the radio telescope. It took us 2 years, covered an area of 57 tennis courts. And this is the finished article. It looks fairly simple. It was fairly simple. It's lots and lots of strands of wire with signal then going into coaxial cable and so on. The most obvious thing are the wooden posts. These are simply to keep the bare copper wire up above long, wet grass, which would be an electrical short. There were about 6 of us built this between us, and as I said, I was responsible for all the cabling. Operated as an interferometer. You could put phase delays between the different rows, kind of turn it into a blazed diffraction grating as opposed to a flat diffraction grating. And that was done with cabling. And we had receivers that worked with what the British called valves, these things. Transistors, no, noisy, unreliable things, too new. We use valves, said Cambridge, proudly. So having spent the first 2 years of my 3 years building the radio telescope, I'm then at last getting close to the science. The science behind this was to find more quasars, quasi-stellar radio sources. Around, well, just a few years before this, Martin Schmidt on the left and Jesse Greenstein had got optical spectra of these peculiar objects called quasars because they looked stellar, quasi-stellar. And they were trying to make sense of the optical spectra. And Martin Schmidt in particular is struggling. Jesse along the corridor is doing slightly better. He has a spectrum of a different quasar, and he's trying to write a paper explaining why the quasar is full of molybdenum because that seemed to be the thing that nearest fitted the spectra. And Martin is looking at his and he says, it looks like hydrogen, but it's way in the red. Could it be hydrogen that's red shifted because the object is moving away from us, giving a red shift? It's a very large red shift. And he goes along the corridor and talks to Jessie and says, Jessie, could your spectrum be hydrogen with a large red shift? And they realize that they have spectra, 2 spectra, with different but large redshifts. These quasars, quasi-stellar objects, are at seriously cosmic distances. And we're probably seeing them as they were quite some time ago, early in the universe. So around about the time that this story begins, quasars have been recently identified as very distant objects and giving us information on the early universe. And they're objects that radio astronomers can pick up very well. And they're apparently very compact objects. And because they're compact, they suffer what we call scintillation, a kind of fluctuation in the brightness. So the fluctuation in the brightness, there's a quasar you have to imagine is away above the ceiling. Down here is the Earth radio telescope. Sun is off on the left and the solar wind is blowing out. And the solar wind is not smooth, but contains clouds of increased electron density. And as the radio wave from the quasar comes through this, it acts like a diffraction screen and the beam gets split. And it's a moving diffraction screen. So what the radio telescope picks up is a rapidly fluctuating signal. That's about 1 second. Radio galaxies are much more extended, and you see them through several of these clouds and several gaps, and so they give a steady light. So you can pick out the quasars by the fact that they show this interplanetary scintillation. And that was the basis of the technique behind the radio telescope. So I spent the first 2 years of my 3 years helping build the radio telescope. And then in the 3rd year, the others melted away to other projects. And I was left to operate the telescope and to analyze the data. We hadn't access to a good computer. University had 1 computer, occupied a room this size. Very few people could have time on it. Laptops had not been invented. Even desktops had not been invented. So our data comes out on paper chart, miles of it, kilometers of it, 30 meters every day, 4 days to scan the sky, so 120 meters for a sky scan. And by the end, I had 5 kilometers of this stuff. And I'm looking for something, a radio source that fluctuates rapidly, which would be a quasar. So I've probably said most of this. Observed for 6 months, the first 6 months use of that telescope, and found a lot of quasars. Got the number up by about a factor of 100. But remember, I'm in Cambridge. I'm not Southern English. I've not been to the right school. It's a scary place. Everybody's terribly brilliant and absolutely confident and swanning around the place. And here's me from Scotland and Northern Ireland and female. And so I'm being really thorough. And as I scan these kilometers of paper chart, I begin to notice another signal. For the radio astronomers present, we have high pass filtered the data because we're interested in the fluctuations of the quasar signal. So we've lost the sort of big drool of the main signal, and we've got just the high pass, high frequency stuff. And this is a little bit of the charts. This is some of the high pass stuff, and there's a lot of noise. There's a little bit of interference here, and there's something that looks slightly different there, which turns out to be the first observation of a pulsar. For any students in the audience, when you say these look different, You're actually doing a Fourier analysis in your head. Here you can see space between the spikes. You can see the chart. Here the spikes are jammed very closely together. Here the spikes go up and down. Here they largely go up. That's why they look different. But spikes going up and down, or spikes only going up, is a comment on the amplitude. Spacing between the spikes is a comment on the frequency. So you've done a frequency amplitude analysis or a Fourier analysis of the signal. So the first few times I saw something like this, I will have logged it with a question mark. And it didn't always show when we observed that bit of sky. But after a few sightings, my brain said, you've seen something like this before, haven't you? You've seen something like this before from this bit of sky, haven't you? And then it's easy, because I store the rolls of paper by which strip of sky, which declination it is, and I keep them in shoeboxes, each labeled with the declination. So you find the shoebox that covers this declination, you heave it out, and the grad students worked in an attic, which was probably a bit longer than this room, and there was a much wider aisle, but it was absolutely splendid for spreading out rolls of chart paper. So I unrolled my chart paper down the aisle, lined them up by right ascension, and said, this is the one I've just seen. Nothing there. Wait, it might have been there. No. Yeah, that's the one I noticed last time. And look there. When it's there, it's at the same right ascension, and these are all the same declination strip. It's from a constant bit of the sky. I convey this information to my thesis advisor, who is not terribly impressed. He basically says, you stupid fool. This signal is so compressed we can't see what's going on. We need an enlargement. With this technology, enlargement is easy. You run the paper faster under the pen and it all gets spread out. But I can't leave it running at that rate because it'll get through the roll of paper in 20 minutes. And guess who lives at the observatory putting a fresh roll of paper in every 20 minutes? So next best idea, grad student goes out to the observatory about this time, switches to a high-speed recording, stops it about there and lets the telescope do the rest of its work. And I did that for quite a few times and made high-speed recordings of receiver noise. The thing, whatever it was, had gone away. And my thesis advisor was not pleased, and of course it was the fault of the grad student that she hadn't got it. And then one day I did. The labeling is later. We'll explain that. This is the very first signal that I picked up. And I had 1 second time pips. There was a radio station in Britain that gave time signals. And you can certainly see along here, blip, 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 blip. There's probably a pulse missing there. Those ones seem to be on phase. Several missing here. And these are on phase. And the period is a little bit over 1 second. So I convey this information to my thesis advisor, who really is not impressed. You've done something stupid, Jocelyn. You've wired it up wrong. Comes out to the observatory the next day, stands looking over my shoulder as I wire up for the special recording. And fortunately for me, the thing performed and in came a signal like that. It was pretty marginal for detection. We now know it was scintillating, but no guarantee that you'd be able to get it. But fortunately I did. And we established pretty quickly that the period was much the same as I'd seen on the previous day. So, right, Jocelyn, you will keep observing this thing, which means Jocelyn goes out to the observatory each day, 15 minutes before this thing's due to transit. And one feature of the night sky is it gets 4 minutes earlier every day. which is fine if you're working from 6 p.m. to 6 a.m. But once it gets into the early hours of the morning, it's interesting. But we did that. I think mine was the nickname Little Green Men, totally in jest, simply because you had to call it something. The one tells me that this label was added quite a bit later, because you don't call the first one number one until you have more than one. So that's later labeling in Tony's handwriting. So local radio interference. This is a massive collecting area, 57 tennis courts. It picks up any interference that's going. So is it interference? Well, no, because on subsequent days we found it at the same sidereal time. It's keeping its place amongst the constellations. Is it faulty equipment? We asked a colleague, Paul Scott, and his graduate student, Robin Collins, who had a separate radio telescope also operating at 81.5 megahertz, could they see it? And I vividly remember this test. There was Robin and Paul, his supervisor, and Tony and I. My telescope saw the thing first. It was pulsing nicely. And then we all went and stood by Robin's pen recorder. And Robin had said it'll appear about 10 minutes later. And nothing happened. So the two academics, Tony and Paul, start walking down this long laboratory. What could it be that shows in your telescope but not ours? Could it be? No, it can't be that, because have you thought of it? No, that won't work. Well, Robin stays by his pen recorder and I'm trying to keep up with this conversation. And suddenly there's a shriek from Robin, "Here it is!" We all went charging back up to his pen recorder. He'd miscalculated by about 10 minutes when his telescope would see it. If he'd miscalculated by half an hour, we'd have all gone home and the story would be different. But it's picked up by a separate radio telescope, so it's not that I've wired ours up wrong or anything like that. And it became clear that as I observed it day after day, it was keeping the same pulse period as accurately as I could ascertain. But the pulses were all quite short and steep, so it was small. Now, to keep a pulse period accurately, it's got to have big reserves of energy. So it's big, but it's small, which doesn't make sense. We now know that neutron stars are small, extremely dense, and big in mass. A colleague borrowed my radio telescope, retuned some of the receivers to slightly different frequencies to see when the pulse came in at the different frequencies, which gives you a measure of what we call dispersion. Higher frequencies travel faster through charged media than lower frequencies. So how much earlier is the higher frequency signal compared with the lower ones? Make a guess at the number of electrons in interstellar space and get an estimate of distance. And it's away beyond the sun and the solar system. It's out in the galaxy somewhere. 200 light years was the distance that John Pilkington came up with. I had nicknamed these things Little Green Men, and just to entertain that suggestion a little bit further, if it were little green men, they probably lived on a planet that went round their sun. And as they go round their planet, there'll be Doppler shift. Pulse period is shorter as they're coming towards us. Pulse period is longer as they're going away from us. So Jocelyn, keep making observations. We're going to look for the Doppler shift. And we found a Doppler shift. But it was due to the motion of the Earth round the sun, because Doppler shift works for the observer as well as for the source. So we'd proved the Earth went round the sun, but otherwise weren't making a lot of progress. And then one evening, grad students work quite long hours. One evening I was trying to catch up with the data analysis on the quasars, scintillating quasars. And I'm sitting looking at a piece of chart, and suddenly I see a signal rather like the one that we've been chasing. It's from a totally different part of the sky, a different declination strip. I file these charts in shoeboxes by declination strip. So I heave out the box that covers this bit of sky, spread out the charts on the floor of this very long attic, line them up by right ascension. So here's the one I've just seen. Wasn't there, might have been there. Yeah, no, yeah, didn't notice that, it's clear there. And it's clear there. And they're all at the same right ascension. And this is the same declination strip. Wonder, is this one another of these? Give my supervisor a slightly cryptic message and head out to the observatory, because that bit of sky is going to be observed in a few hours' time and I need to be there. And switch to the high-speed recording and so on, and in comes pulse, 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 pulse. Not quite the same period. The first one was 1.3 seconds. This is 1.2, but near enough to be, you know, the same thing, and from a totally different bit of sky. So it's not little green men. There aren't two lots of little green men signaling at Earth. This has to be something natural. And in due course, I find two more. The fourth one was perhaps, well, I could just carry on with the story. I found that second one at about 3 a.m. before I took the Christmas break and went with my boyfriend to announce our engagement at my family home in Ireland. Came back proudly sporting an engagement ring. You'll notice this finger's naked now. Proudly supporting an engagement ring, which was the stupidest thing I did. Because at that time, married women did not work. And this engagement ring was a signal that I was going to be giving up, which my supervisor noticed. Come back after Christmas. Tony's very kindly kept the survey running. He's put fresh paper in the chart recorders, ink in the inkwells, and there's an enormous pile, a pyramid of charts for me to analyze. He's in a meeting, so okay, I sit down, start working on analyzing. Oh yeah, which one's that? It's not either. Wow, might be a third one. Crikey. Okay, there's only 30 centimeters left of this chart paper. I'll finish this roll of chart paper and then we go chasing that one. What? 2? About 20 minutes apart in right ascension? At that moment, my supervisor appears and stands at the end of the desk. Tony, look at this. Oh, Happy New Year, Tony. Thank you for keeping the survey running. Look, 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 look. How many more have you missed? Go back through all your old records. There were kilometers of the stuff, but I duly did. And we ended up with 4 of these things. The fourth one, 0950, being rather exciting because it was pulsing with a period of 1/4 of a second. All the others were 1 and a bit seconds. So we had 4. We wrote up for publication the first one, and the other 3 would follow in a subsequent paper. Martin Ryle phoned up the editor of Nature and said, sort of, hold the press, we've got an interesting paper coming. And they did publish it very, very quickly. And the reaction was huge. Just before the paper was published, Tony gave a colloquium in Cambridge, gave it a very titillating title, and every astronomer in Cambridge came. And Tony went through what we'd found, what we'd done, and so on. Tony had 2 possible models for what could be causing the pulses. Yes, it could be what we now know was the answer, something rotating with a radio beam that gives a pulse each time it shines on the telescope. or it might have been an oscillating white dwarf, which somehow is launching shocks into his atmosphere, which somehow is giving flashes of radio waves at quite regular intervals. The acid test is how the pulse period changes with time, because if you've got something vibrating, as it ages, it quivers faster and stops. Whereas if you've got something rotating, with time, it slows. So is the period increasing or decreasing? We didn't have a long enough baseline to answer that question, but Tony was preferring the white dwarf launching shocks. And when he gave this colloquium in Cambridge, that was the model he presented as the preferred picture. As I say, every astronomer in Cambridge was there, including Fred Hoyle, who sat, so to speak, in the front row. And at the end of Tony's colloquium, Fred was the first to speak. Fred, for those who don't know the astrophysics personnel, was a rather crusty Yorkshireman, inclined to the blunt statement, but an extremely good physicist. And Fred was the first to speak and said, "I don't think it's a white dwarf. I think it's a supernova remnant," in his Yorkshire accent. And it's a measure of the ability of that man that within 40 minutes, he's digested all the information and hit the right explanation. Because subsequently, they did turn out to be neutron stars, rotating neutron stars, which with time gradually slow. This was the first detection of neutron stars. They'd been described by some mad theoreticians, but no, let's see if I jumped. Yep, okay. Following the announcement in Nature, there was considerable press interest. And when it was recognized that there was a young woman involved, a whole new sector of the press became interested. And I, in particular, got asked questions about what were my bust, waist, and hip measurements, how many boyfriends did I have, would I describe my hair as brunette or blonde? Not a scientific question amongst them. Tony got all the scientific questions. And I was the sex appeal, I guess. It was really rather horrific. The photographers were quite the worst. Please, could I undo some more buttons for the photograph? That kind of thing. It was horrible. But one of the delights of having been involved in this is every so often somebody comes up to me and says, I nearly discovered pulsars, and tells me the story. And I think those stories are as revealing. So if I could have a few more minutes, I will tell you some of these nearly discovered stories as related to us. And the first one is a way back in 1957. We're in the USA at the McDonald's Observatory. McDonald's has given money for an 82-inch telescope on condition that the observatory is open for the public one night every month. And this is the open night. And the telescope operator has set the telescope on the Crab Nebula, which is a fuzzy patch of stuff in the sky with at least one sort of star-like thing in the middle. And he set it on that star-like thing. Ancient Chinese observed an exploding star at that site, a supernova. And so the nebula is the debris from that explosion, and the pinprick of light in the middle is the remainder of the star that exploded. So people step up to the telescope and say, gee, wow, whatever they said in 1957 in the USA. And a young woman steps up to the telescope and says, that star's flashing. And the night assistant starts to explain about the way stars twinkle or scintillate. And she stops him. She says, no, I'm an airplane pilot. My job is to fly newly constructed aircraft from the manufacturer to the customer. I fly at night. There's not a lot to do in the cockpit at night. I know about the scintillation of stars. That star's flashing. Now, the crab pulsar does have optical flashes at a speed of 30 hertz. Not many of us can see 30 hertz, it's too fast. But the people most often who can are young women. In Canada, they used to have the main power supply at 30 hertz, so all the lights and the television and everything used to flash at 30 hertz. And some people, particularly young women, could see the flashing. And it nearly drove them crazy. And ultimately, they moved to a higher frequency for their power supply. But some young women can see 30 hertz. Sorry? Physiology, sir, I don't know. It does seem to be largely young women that can see it. Yeah. So she says that star's flashing. But yeah, okay. Next person, please. No follow-up. But this student who was working there for the summer remembered and told the story. I used to have, he ultimately moved to Socorro in New Mexico and was known to be there. I don't think he was an astronomer. I think it was by chance that he was in Socorro. Yeah, we did know. And he confirmed the story to other radio astronomers. So I'm not the only one holding the story, so to speak. But nobody followed up. That was 1957. In June 2007, the Australians, who by now have an online Pulsar catalogue, get a very excited email from an elderly US gentleman called Charles Schisler. He had done a stint with the US military. He'd been based in Alaska at the early warning site there, you know, looking for missiles coming in from Russia. And when things were deemed to be quiet, his boss allowed him to play around with the equipment. And he used the receiving equipment to see what things there were in the sky. And he found some flashing sources. He'd done an astronomy course at college. Bless that college. He'd learnt about right ascension declination. He made a note of the right ascension and declination of those flashing objects, and absolutely illegally taken that little bit of paper away with him when he left the military. He's now discovered the online Pulsar catalogue, and 14 or 15 of his flashing objects have pulsars reasonably nearby. But of course, he wasn't able to publish. But he had a whale of a time linking up with the Australian radio astronomers. So that's him in the background at a conference dinner. So, yep, 10 or 11 of them have been identified as pulsars. And one was the Crab Nebula. I doubt if he's still alive now, but he certainly had a very happy senior citizenship when he made contact with the pulsar astronomers. The last example involves Sue Simpkin, who was Canadian, maybe still is Canadian, lived in Canada at the time that their lights power supply was at 30 hertz, and was one of the young women who could see 30 hertz. She's doing ultraviolet spectroscopy by this stage. Dutch astrophysicist Lo Vulture asked her to take an ultraviolet spectrum of that funny star in the middle of the Crab Nebula, which we now know is the pulsar. She duly does this. She says the spectrum is boring, but as she observes it, she can just see what she describes as waves coming out from it. And given that she can see 30 hertz, and the Crab Crab pulsar goes at 30 hertz, she's probably seeing something associated with the pulsar. She describes this to Lo Vulture, who is not impressed. But when a few years later, the Crab pulsar is discovered and announced, he's man enough to say to her, "You probably saw it, you probably were right." The final example I'm not going to name because they were acutely embarrassed, remained embarrassed ever since. So some radio astronomers are doing an all sky survey using borrowed radio telescopes. They get, 3 nights on this telescope, 10 nights on that one, 5 nights on that one. And by doing this, they have gradually put together a map of the whole sky at 408 megahertz. But inevitably, when you do this kind of thing, there's some little bits you've missed that you've got to fill in. And they're in the last stage. They're filling in these bits. It's quite old technology. They use pen recorders. They don't have anything more modern than that. And very near the end of their observing, one day at 3 o'clock in the morning, when it's really the worst time of observing, one of the pen recorders starts going whoop, 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 whoop. That pen recorder was known to be troublesome. It was a bit sticky. So the observer did what we always did with pen recorders. You thump it and it unsticks it, as it did this, because the pen stopped going whoop, 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 and went back. And the observer said, good, put on his coat, went home to bed without making any entry in the logbook. We now know that they had been observing a pulsar 0329 plus 54. But because they had no entry in the logbook, they couldn't claim prior discovery. So logbooks sometimes are very important. Probably about 1965. I think so. I was discovering pulsars in 67, 68. So it would have been prior discovery. Yeah. So I think I've told you all that. So it was the pulsar 0329 plus 54. A pulsar that never sets in the UK, which is handy. A circumpolar pulsar. I want to end up by paying tribute to Franco Pacini, whom a number of you may well have known. At the time, mid-1960s, late 1960s, the Crab Nebula was a considerable puzzle. It was known it was the remains of a star that exploded in 1054 AD. There had been good observations. And the nebula was sort of the mess of the exploded star. But that radiation, the remains of that explosion, really ought to have faded from sight long ago. And yet this nebula is still one of the brightest things in the radio sky. Why has it not faded, given how long ago 1054 was? And it was a puzzle that various people tried to solve. And Franco Pacini, in advance of the discovery of pulsars, had hit the right explanation. He said, in the Crab Nebula, this is the nebula here, in the middle, there is a neutron star. It's the core of the star that exploded, and in the explosion, the core gets compressed, makes a neutron star. It's a highly magnetized neutron star. That's plausible. As you compress something, you might compress the magnetic field as well. And there is an inclination between the spin axis and the magnetic field direction. And as the star spins, there is what we call magnetic dipole radiation at the rotation period. Now, depending on the electron density in the nebula, but if the electron density is high enough, that radiation may not escape the nebula. It may get dumped in the nebula, keep the nebula energized, keep it shining. So he was right, absolutely right. And this was in advance of the discovery of pulsars. He was an incredibly good scientist, as well as being a great man. Just briefly, the factors that I think led to the discovery when it happened. We had our own telescope and receiver, and I made it my business to understand how they all worked. As a grad student, you have time, you've not much else to do. But I also had this imposter syndrome. They're going to throw me out. They've made a mistake. This was one of the first observations with high time resolution, with a short time constant, because we were looking for this scintillation, twinkling of quasars. We weren't aware of any other observers doing similar work, so we didn't feel under pressure to rush the result out tomorrow. We could take a little bit of time to be absolutely sure we were right, which gave me time to find several, which made the whole thing a lot more plausible. In terms of getting published, we had a good address. We're not crazy. This matters a bit, particularly with referees. Shortly after that time in Britain, there was great emphasis on what are your objectives? What are the targets of your program? This wasn't one of the objectives. It couldn't be. We didn't know it had existed. If we had been in that regime, would we have been marked down for deflecting from our goals, our targets? Sometimes these civil service things can get quite crazy. More seriously, if we had computerized the search, given how limited computers are, we wouldn't have bothered to look for fluctuations that fast. And although now things, because of telescopes like LOFAR, are coming online, for a long time subsequently, low frequencies have been neglected. And time domain has not been neglected so much because there's a lot of pulsar astronomy, but it's a bit of a specialism, I think it's fair to say. So thank you for your interest, thank you for your attention, and thank you to the Society for very many kindnesses. Thank you.
Thank you very, very much. This has been intense and great. And are you willing to take questions?
I will try to answer questions.
Okay. So please, any question?
I'm intrigued by this comment by Fred Hoyle when he commented on the first sight of these pulsations. He immediately thought of a remnant of a supernova, because of course Fred Hoyle worked a lot on the theory of it. So was he aware of Franco Pascini paper, which appeared a few months earlier, or was a completely independent comment?
I would assume he was aware of Franco's paper.
Oh, I see.
He was quite widely read.
I see.
Unless, of course, as happens with many of us, we have a backlog of about 6 months of papers that
Yes.
we ought to read. But I don't actually know for sure. But Fred was pretty good at keeping up with things through what he read, but also through conversations over coffee.
Right. That's interesting. And also this detection a couple of years earlier in 65. So why were they observing? What kind of radio telescope was that?
Was this the survey one where they were?
The survey.
Yeah, I think it was 408 megahertz. They were using telescopes wherever they could get, radio telescopes, wherever they could get time. I think they were observing at Jodrell Bank because the relevant stuff is in the Jodrell Bank library. So I suspect it was at Jodrell Bank.
But why did they notice only once these pulsations? I mean, they could have noticed the recurrence of these pulsations.
I'm not sure that they repeated the patches of sky. I mean, once you've done the survey, you think you've done the survey and you don't reckon on time variable stuff.
Yes.
Enrico.
Just two comments. So one is about how you were able to discover a fast phenomenology in an epoch where nobody would expect a anything so fast from a celestial object. There is an analogy with the discovery of gamma ray bursts. They were discovered by a military satellite, and only this could be the source because they were equipped with instrumentation to make very fast detection of events just to probe nuclear bomb experiments.
Yeah.
And also they were set in such a distant position in orbit to be able to detect the direction through delays.
Yes.
And this was also a case.
And they had, I think, 3 satellites monitoring at any one time so that they could position. Yeah.
Yes, and also checking nuclear bomb testing in the dark side of the moon. That was somehow a paranoia of Cold War times.
Yes. Yeah.
But another point is that you mentioned that Franco Pacini was lucky that he was in my institute when I went to make my graduate. And you know the story of Franco Pacini. He was a fanatic amateur astronomer, and his dream was to become a professional astronomer, to have the capability to look stars at the ocular of the largest telescopes. And he was entitled by Professor Grattan of a thesis on spectroscopy of K giants to probe the amount of metals in the universe, in the galaxy, because you can go far from us. And one day he got a box with the plates that were something like 20% of the throughput of the largest Italian telescope with the spectra of K giants. And he folded and he broke all these lights. And Professor Grattan was really furious. After a few days, he became quiet and put a hand on the shoulder of Pacini and said, "Pacini, you will be a theoretist. Take this paper with the radio emission from a white dwarf with magnetic field misaligned with the mechanical axis, and you recompute everything for a neutron star instead of a white dwarf. And this is your thesis." Actually, I had already given this thesis to Miss Caloi, but never mind, I gave her a thesis on photometry of open clusters. And this is not a legend because Pacini used to repeat this publicly also when there was the retirement of Grattan. He explained more or less as I have reported. It looks more a legend, but it's absolutely true.
Yes. Yeah. Thank you for that story. That's great.
Grazie. The 2 previous speakers have already agreed to have their summary of the lecture in Italian written for publication in the journal of this academy. You probably have already spoken or published your results already. Would you be so kind to write down, of course in English in that case, your description of the facts for to be published together, or otherwise, if you have published it already, would you permit it to be summarized, translated into Italian, and published in our scritti and documenti?
If you can organize the translation into Italian.
Oh, yeah, no problem.
Very happy with that. Thank you.
Okay, I accept your kind answer, and I add one more point. They said they need all the summer to prepare their Italian scripts. How long will it take to you to send to me the English script of yours that I might translate it?
I'm not sure about the answer to that because at the moment I can't remember what my next commitments are, but I will do it as fast as I can.
Okay, then I give you a little thing that you might not know it. You have received the Copley Medal.
Yes.
Well, Matteucci too received the Copley Medal in 1832, which means that he is the only Italian who had it.
Really?
But you stole my act, you know.
Sorry.
Yeah, okay. You are a president, honorary president, so it's fine. Okay. So may I close? Are there any more questions? No. So I think that it was a very pleasant morning, at least for me, certainly. And Jocelyn was very, very interesting. Also, the way people worked 55 years ago. I mean, and I remember, spending times in work in the library, reading all the materials and the journals. Now I think nobody reads the journals anymore. They are just for the only, scope of journals is to allow people to say, I published in that journal. I mean, it's nobody. And so it was, for me, it was very, and of course, what you got is fantastic. So thank you again, and thank you to the committee of the medal. It was, I think, a very enriching experience for the small academy. Thank you.
Thank you very much.